Awesome. Thank you. Welcome back, everyone. We're now officially on week 3 now. Sorry for the sick day that I called on the Monday class. I was telling some people in class earlier, I was feeling great Thursday after class ended, but then Thursday night I felt a bit off. Friday morning I felt like crap, and I actually went to the doctor. I was thinking it was the flu. Turns out it was COVID, and they told me to not come back to class if I still had a fever. So I didn't want to infect anybody on Monday. It's probably going to be okay to teach on Monday. I actually did my 6 to 6:50 class, but it's fully online, so I didn't see the danger in that one. But I just didn't want to risk it. It wasn't a fun experience for me. It felt like the flu, but turns out it was just that. But welcome back, folks. I hope you all got the announcement that class was canceled. It kind of sucks if you have to, especially drive kind of far out to here and just find classes canceled. I made an announcement and I also made the email message to Canvas as well, just to make sure you hopefully got that message. But any questions at all, folks, to start us out today? Okay. Well, we're starting week 3 a little bit late, but we still have 2 good days out of that. So it's still going to be a week that counts. A lot of people have turned in their quiz 1 already. And like I mentioned, you can turn in a lot of ways. So far, I've got a good set of hard copies, and you can always just drop them down here at the start or at end of class. They'll work out just fine. If you're working digitally, you can convert it to a PDF and send me an email. Anything like that works. And if you had it and you just forgot to hand it to me, but you go home and it's just sitting there in your hand, just take a picture of it, scan it, send it to my email. That works out just fine as well. So we're going to be posting our second quiz when we come back on Tuesday's class. It's going to be based off the section 2.4 here that we're working towards. But maybe another big announcement for us is we're on week 3. It's a good time to see how the course fits in with the rest of your classes, kind of like we mentioned in week 2. We're starting to get in a stride, even though I took a sick day on Monday. Then week 4 is going to be a normal full week. Hopefully, no weird emergencies. Usually, it's pretty rare for me to take sick days. And week 5, we're going into our first exam week. So what I'll be doing this weekend is I'm going to say what the definite coverage is going to be for the first exam. It's probably going to go up to section about 2.5, but I'll know exactly where we're at when we finish out Thursday's class. And if you're the kind of person that wants to take a look at some sample exam questions early, these are 2 different versions you could start taking a look at. It says early draft because I might take some questions off or add some questions on just in case I don't have quite the right sections here that I thought I might have. So everything is going to get finalized across this weekend when we come back on Monday's class here. We'll talk a little bit more about exam 1 then. But anyone have any questions about it so far? Yeah, it's like one of those things. It's just kind of a formality. It'll be like a normal class. We'll all be here. I'll just be really quiet that day. And so it'll just seem kind of strange, but we'll get through it. It's a 75-minute exam, which feels brutal, but I'm not in the habit of writing exams where you're working all the way down to the minute. It's going to be more like a 50-minute exam with some built-in time to check your work. So we're not going to try to overload this exam with a bunch of concepts. And if you took a look at these early, they look long, but I'm just giving you an idea of what questions could be asked on the exam. I'm not going to be asking you 18 pages of material. So think of this as more of a study guide. If I'm going to ask a chapter 1 question, it's probably going to be just 1 or 2 questions. They'll look about like these that you see here. These are all brand new questions on the first file. And if you scroll all the way to the very bottom, the stuff in green is the solutions to those same questions. So you can check your work as you start working those problems. So that's version 1. These are all fresh, brand new problems. So a lot of people like this document quite a lot. But version 2 is a good one too as well. Version 2 just will give you a little bit of a sense of deja vu because it's the same exact material as our own actual lecture notes. But sometimes it's good to see these problems again for the second time. Sometimes the second time you see these problems is when those ideas really connect. So what I've also done on these notes is notice how it starts at example 2. It's my way of saying, well, example 1 of the notes didn't make a good exam question. This is a better version of what could really show up on an exam. It goes by section. It doesn't have the solutions at the very back, but you would find the solutions just up here when we complete the notes, because these are the solutions to those same exact problems. So these will be posted a little bit earlier in case you want to start reviewing your notes, those kinds of things. But for the moment, again, it's probably going to be from chapter 1 up to section about 2.5, and we'll know the definite coverage after Thursday. Well, we left off finishing section 2.2, so now we're in section 2.3. This one's a shorter section. Sometimes they're pretty long, sometimes they're pretty short. And this one's the longer section right after. So we'll probably be getting through section 2.4, starting it today, finishing it on Thursday's class. So section 2.3, kind of a rehash of what we did in section 2.2. 2.2 is about displaying a quantitative variable. And here we're just looking at it for a second time, really just focusing on the histograms fundamentally this time. When we go to analyze a histogram, an often question you might just see as an ordinary quiz question potentially or exam question is just describe the shape. And that's a tough question in a certain sense unless we know what we're being asked. Whenever you're describing the shape of quantitative data and you see a histogram, like the one down below, shape really has three different things we have to address. How many peaks or modes does it have? Is that unimodal, bimodal? Those kinds of concepts we're looking at from last class. We want to know whether it's symmetric, skewed left versus skewed right. So we'll look into that kind of information again. And we're also always on the hunt for outliers in the data whenever we see them. So all these data have no context. We'll look at two problems that do actually have context that might be more interesting. Here, we're just focusing primarily on the shape. So we have some sample, that's all it says, sample. It could be heights, it could be times, it could be miles. This goes from a negative to a positive 3. And frequency is just telling us if we say focus on this section right here, from -2 to say -1.5, everything in this region, we count about maybe 40 individuals. So that's what the frequency scale is telling us here in that direction. But really our main question is, what is the shape? So first thing we address is how many modes or how many peaks does it have? What would you all say this is? Unimodal, bimodal, or trimodal? Yeah, absolutely. This one just has one main peak. The data is all accumulating in this one little spot here. So this would be unimodal. Then next thing we go through is whether we think the data is symmetric, skewed left, or skewed to the right. But these would be, like we mentioned in the other examples we saw, really super symmetric looking data. It's rare to see data this nice. And the way we can tell just as a review is, if we have it unimodal, then there's one main peak. Go to that peak and put in a dashed line. And if you can roughly fold the paper across this dashed line and have the heights of the rectangles lining up, not perfectly, but roughly lining up, you're looking at symmetric data. So these would be unimodal, highly symmetric, and, well, that's so far so good. All we need to say about the shape is whether there happens to be any outliers. Anyone spot any outliers for this data set? So I'm shaking their heads no. Yeah, I agree with this one. An outlier would mean there's some case that just looks insanely different from all the others. Like, for example, if we had data way out here, away from the main path. But all the data accumulates at the main peak, and in a regular way, it just falls away. Cases become rarer and rarer. Individuals in the sample are less likely out here. But these aren't outliers. That's just the normal pattern of the symmetry we're seeing. And same going off to the left. So we'll say here, no outliers. Still, this is all just based off visual inspection. This is subjective based on what you see. We'll eventually get formulas for finding outliers like we mentioned before. And I mentioned that a lot because it is kind of uncomfortable to try to make that determination. with no formulas on the table. So this is like the best case scenario of the data. And for the other parts of example one, we're just looking at all the other weird things that can happen. This next one is really weird. So here's some other new data. We've never saw data like that until just today in this class. And we're still addressing what is the shape of this data. First thing we have to decide is that unimodal, bimodal, trimodal? But you know there's another category here. Sometimes the data has no modes. There are no main peaks whatsoever. Just because there's random changes a little bit up here, a little bit up here, doesn't really mean data is aggregating there. That could just be to random sampling alone, random effects in the data. So these data would have no modes. And we would give this kind of data a specific name. This is uniform. So uniform data takes this kind of shape. The way you might get uniform data is this could be an experiment where you have maybe computer technology, pick a random number between 0 and 1 and give you that random number. That number is random and unbiased, and you run that experiment over and over again, collect those numbers. This is about what it would start to look like. You would get random numbers with an equal chance of being close to 0, an equal chance to being around 0.5, an equal chance to being close to 1, and so on. So it's just completely random, no pattern, where the number would have came from. So this kind of data set matches random numbers between 0 and 1, where no number has any extra bias. No number is more likely to appear than the other. So it's totally uniform, no modes whatsoever on this one. How about for symmetry? Would you call it symmetric? Yeah, definitely. It's not the symmetric shape we've been hinting at a lot in class, like this one right here, but it's still symmetric. If you go to the center, 0.5, it might be even more symmetric than the last example. Things fold over and are very close to the same heights once you overlay them across this line of symmetry here. So this is uniform, highly symmetric. And just like before, all of the information is kind of close to each other. Nothing is far to the left, far to the right. So there are no outliers for these data. So data like this can occur. It's weird when it happens, but it's not as rare as some other things like, say, left skew data we mentioned in the last class. Any questions at all, folks, with the uniform data? Okay, so other data can occur. This one's not as unusual. It's just problematic data, like we mentioned before. When data like this occurs, we sometimes have to work a little bit harder with statistics. But still, it's easy to say what the mode is. There is one main peak right here. So we would say that this data is unimodal. We'll get something that's not unimodal and not uniform on the next example if you're curious. Next thing you have to decide is if it's symmetric, but would you all agree absolutely not symmetric this time? Yeah, symmetry is broken in a huge way. Symmetry means you're usually going to the one main peak, trying to fold it across this dashed line. But if you did that, data over here, when it folds across, has nothing to match up on the left-hand side. It doesn't matter where you put the dotted line, things are way off. Symmetry is just totally broken in this example. That means it's skewed. Anyone recall which direction this would be skewed to? Is it skewed to the right or to the left? Yeah, absolutely. The skew is the direction it trails off in, and it starts trailing off here, here, here. Another case way over here. So we would say these data are skewed right due to all those individuals trailing off in the positive direction. You might not have said skewed right. You might have said positively skewed. That would be just fine as well. I usually just say skewed right or skewed left. Positively skewed kind of makes sense. It's in the positive direction of the x-axis. If you like thinking in those kinds of terms. Still, it's not the full story of these data. What else would you all want to mention when you saw something like this? Yeah, we have data way out here. It is pretty far off the main grouping of data. You don't have to decide if you want to say it's a super extreme outlier versus a mild outlier. As long as you call it an outlier, that's good enough. So here, just in case you're wondering, I wouldn't say it's too extreme, not like what we saw in the last notes when we're looking at Florida campuses. That one was completely out of the line with what we saw. This one definitely looks unusual, so we'll say, well, I want to say one apparent outlier, but you have to admit, the scale's not super helpful, right? There could have been a couple people in this category. I'm just not sure. They don't give us enough visual information to really tell. And zooming in is not going to really tell us. If you said one outlier, that's going to be all right with me. But I'll say at least one outlier just to admit, I'm really not sure. It could have been one, maybe two, could have been three. It's hard to tell. So let's say at least there is at least one outlier in that region there above 8, whatever the sample had to happen to have been. So these so far are some of the main ways we'll see some of the data. This one's pretty unusual. I think we have to work pretty hard to see uniform data come up, but it can happen. So it's here just for reference. And then next one is bimodal data, like this over here. So I guess I gave away the punchline on this one, but these data would be absolutely bimodal because we have one peak here. Lots of data aggravate here below 0, and we have another peak. So we can say altogether, these are bimodal data, or you could have just said there are two modes. That's fine as well. You don't have to say bimodal, trimodal, unimodal. You can just say one mode, two mode, three modes. But these words are more common in the reading, so it's not a bad habit to say it that way either. Bimodal data is kind of tricky in a way because usually when the data is bimodal, there's a categorical variable there. Maybe you already knew what it was. Maybe it had to do something with the gender or the sex of the organism we're looking into. Maybe this is about birds, for example, and we're looking into mass. That may not make sense with negative here for negative mass. But usually there's some kind of categorical variable in the background. And what you would typically do is start to try to separate things out. Maybe one category of individuals belongs to this main peak. Another category of individuals belongs to this other peak over here. Maybe there's genuine overlapping in the middle where individuals cross a bit. That doesn't really overlap too well in the color coding. So usually this kind of implies bimodal data. Often, but not always, it often implies a categorical variable describes who belongs to each peak of data. So I think a book had a pretty interesting example where they look at a whole bunch of cereals. So imagine going to Winco, gathering the information on grams of sugar in each box of cereal. If you did that right now, record all the grams of sugar on every box or bag of cereal in Winco, people might ask you some strange questions, but plot all that data in a histogram and it's probably going to look like this. And one explanation of why you're getting bimodal data is on the higher end, that's going to be the kid cereal with super high amounts of sugar for some reason. And on the lower end, that might be the adult cereal that's marketed to be a little bit more healthier, less grams of sugar. That's one natural way things come in as bimodal. The categorical variable would be children's cereal versus adult cereal, for example. It does make the follow-up questions a little bit trickier, though. What would you all say for symmetry on this one? Would you say it is symmetric or is not symmetric? Kind of depends on what you mean, right? Does it mean symmetry across each of the peaks? I would say this one is somewhat nice symmetry. This one is not quite. It's just roughly symmetric, not terribly skewed just yet. But the third thing you could be asking is, do you mean symmetry as the whole thing taken as one, a whole grouping? If that's the case, you might fold across the center like this and see if the two sides on the left and the right roughly overlap. They kind of do. Would you agree in that case? So this one's an awkward question. It just depends on how you decide to answer it, how you're visualizing it. Makes this one probably not the best exam question for that reason. But if you like this view of it, the data as a whole, both of the peaks taken together, we could say these are roughly symmetric. Because yeah, it's true. If you fold across this dotted line, they roughly do match up. Words like highly symmetric, roughly symmetric, not as important because we don't have any formulas for this. So if you just said symmetric, that would have been just fine with me for me on this one as well. Then last, there's no real outliers here. All the data is connected to each other piece of data. So we would say no outliers. So those are the main things we want to think about whenever we're looking at a histogram. Again, the major reasons we do this is later on when we're doing inferential statistics, putting things into our fancy formulas, those formulas all have conditions, things that have to pass. And this is the problematic one. Many of our formulas are going to fail when our data is skewed to this degree. Our formulas don't work on bimodal data the way we would like. We really have to separate out the data, analyze each one separately. So we would have to run two statistical procedures on this. And our formulas work really well for this kind of data, symmetric and symmetric here. But other data like the ones we saw below, those are the ones we take a look at and have problems with. So that's the purpose of looking at all these histograms. We've already looked at quite a lot. We have two more to go in these notes before we go on to the next section, doing something different finally. But any questions at the moment? Okay, so here's a couple more similar problems. This time we have context. That makes it a little bit easier to kind of absorb sometimes. Let me move that over to the left just so that we can, I guess that wasn't necessary. But this one has a lot going on with it. So let's read through this one slowly and carefully. So there was some interesting law that was passed in 2017. It's a fantastic law. And it said public companies, we mean companies traded on the stock market. So like on the Dow Jones Industry, NASDAQ, that kind of stuff. Public companies are required to disclose the ratio of the CEO's pay to the median worker's pay. So if the CEO got paid the same exact amount as the median worker, the ratio would be 1. We should define what we mean a little bit right here already. The median worker's pay is not the same as the average pay. Average is tied in with the word mean. We'll define that in the next section, 2.4, where we define mean and median. But median is its own word. Median means the 50th percentile. So if you get paid the median amount at your company, you are getting the 50th percentile of pay. That means half the workers in your company make less than you. Half the workers in the company make more of you. You're literally in the center now in that sense. Does that make sense to folks of what we mean by the median? Okay. Strangely, it's different from the average, but they're both trying to do the same thing, talk about the center of your quantitative data. This is just a nice unbiased way to do it. The 50th percentile is unaffected by outliers. So it's a nice, robust statistic in that kind of way. So when this says we're looking at the ratio of CEO pay to the median worker pay, we're wondering how wealthy is the CEO getting paid every year compared to the typical employee at the company. That's all we mean by the median worker. So after that law was passed, other like kind of cottage industries just blew up all over on the internet. I don't know if you've been to glassdoor.com, but it's a pretty interesting website. You could look up your own company. You could look up ISU and see what actual ISU employees say about working for ISU. And just about any company now that's available on the internet. It's kind of neat. It's all because this kind of information becoming public makes it interesting. The Glassdoor Economic Research blog has published data for 2014, and they say, with the help of this law in 2017, well, the data includes CEO identities, companies, CEO compensation, median worker compensation compiled by Glassdoor, and the ratio of CEO to worker compensation. That's a lot of information, but we're looking at just one thing, the ratio of the CEO's pay to the median worker's pay. It says again, a ratio of 1 indicates that the company CEO makes the same pay as the median worker's pay. And that might sound nice, but you have to wonder whether side benefits are getting if that's true. This takes into account pay in the forms of like stock benefits and all sorts of other things that seem practically under the table in a certain sense. So pay means a lot of stuff here. A ratio of 1,000 indicates that the CEO earns 1,000 times as much money as the median worker's pay. And that's kind of incredible in a way. This is kind of the land we live in America. And this is the compilation of that data. This is the data that was been constructed since, this is the data from 2004, constructed from Glassdoor. So looking into this, let's zoom into this a little bit better. A lot of companies seem to be right around this benchmark. That's about 400 roughly. So we have a whole bunch of companies in this data set. We hope that this data set is representative of, say, all companies in the United States of America for this to be very meaningful. But going from here to here, containing most of the data, is kind of nice in a way, I suppose. It means most companies have a CEOs that get paid up to about 400 times the typical worker, the median worker. But then when you really look into this histogram, you see some really wild stuff. Maybe Microsoft is in here. Notice that there's companies in the 2000 stretch. It looks like just a kind of a blip here, but that's a real height in this location, just in bold. So there are companies in this data set where the CEO is making now 2,000 times the pay of the typical worker, the median worker in their company. And these companies are pretty outrageous as well, going along this way. So here's some real data for us. It's not symmetric by any means. And oftentimes, if you're taking into account economic data in any form, salaries, home value prices, anything along those lines, you get shapes that look about like this, skew to the right. Well, let's describe the shape. Hard part of these kind of problems is we have to use the context. So that's what's new about this. We can start by saying, well, would you all agree this is definitely unimodal data? Yeah, I agree with you as well. There's blips out here, but that doesn't make a mode. These are unusual cases. So we can say that the distribution of the ratio of pay, I shortened this up. The true name is the ratio of CEO compensation to the median worker compensation, but you can always make that a little bit more brief, like we've discussed before, other similar problems. the distribution of the ratio of pay is unimodal. It's also skewed to the right, like our other graph they were looking at. So because of these parts of the histogram, we would say skew to the right. But here, if you want to use some more clever words to describe it, it wouldn't hurt. This is some pretty impressive skew. We could say violently skewed to the right. This is telling us that there are some companies, there's not a lot of them because this is skewing, this is trailing off data, but there are some companies in this data set where the CEOs are getting paid ridiculous sums altogether. And because of these here, there are also, let me spell also right first, outliers where the CEO is getting paid extreme amounts. And there's all sorts of interesting stories about this. For example, if you've been watching the news, I believe Boeing had to appear in front of Senate to explain why their actual machinists and engineers and those kinds of things haven't had a raise in, I think it was a decade or so, while their CEO keeps on getting additional millions of dollars in terms of raises year after year after year. They drug the CEO in front of the Senate to explain himself on that. Hopefully Boeing kind of redeems itself some way somehow and corrects this kind of picture. Seems like Boeing is probably somewhere in the skewing part altogether. But that's what's going on with this data. Really, the hard thing about doing this kind of problem is bringing in the context. You don't have to say every single bit of it. You could have just said that there are outliers and left it at that. But if you have said somewhere, somehow, we're talking about the ratio of pay. Also, the CEO getting paid extreme amounts is talking about the context as well. Bring in something about the original problem, and you would get full credit on this kind of problem. Bringing in the context is kind of tricky sometimes. It's easy to miss this. So if this was an exam question, I would often put it in bold, just as an extra reminder. Don't forget this part. It's worth bona fide credit on this kind of problem. By the way, if it was an exam question, it might be worth maybe 5 points. The context could be 2 of those 5 points. But any questions at all, folks, looking at these kinds of data so far? Okay, let's take a look at the next example, something more fun, we hope. No, it's acid rain, less fun. These kinds of catastrophizing type of examples seem to be common in statistics, it seems like. That's because people are looking into problems and how to solve them. So that's why sometimes the data looks grimmer than it really is. This data isn't too grim, really. It looks like it's talking about acid rain, and it starts off by saying, acid rain from the burning of fossil fuels has caused many of the lakes around the world to become acidic. If you're watching the news in the 80s, early 90s, everyone was really worried about acid rain, worried about the Lincoln Memorial getting damaged and stuff like that. Somehow it's just not brought up as often, I think. Acid rain is a problem because they tell us that biology in these lakes often collapses because of the rapid, unfavorable changes in water chemistry. And next, a lake is classified as non-acidic if its pH is greater than 6. So those are, I suppose, the good lakes, and lakes harmed by potentially acid rain or something else probably have a pH at 6 or below. So this is just kind of overall context, a little bit of information, background information on pH, why we are a little bit concerned about acid rain. And this is where the data came from. So this is the actual study. I'm not sure I can pronounce that. I'll just go with it. So Marchetto, Lamy, these 2 researchers measured the pH of high mountain lakes in the Southern Alps and reported their findings in this paper here. Reconstruction of Chryso, I'm not sure I can pronounce that word at all. And our spell checker is not happy with that word either. But someone did a research paper, published it in this journal. It says reconstruction of pH by Chrysophysian, sorry for brutalizing that word, scales in some lakes of the Southern Alps. So it's an interesting study because we're worried about lakes becoming acidic. But these researchers were wondering, if we go to a rare kind of lake, rare lakes that are hard to attain, maybe acid rain affected by industry doesn't get to, high mountain lakes in the Southern Alps, they're wondering if they have the same problem with lake acidification. So they went up there. It says the pH levels obtained by the researchers for a random sample, hopefully representative as well, of 15 lakes are displayed in the histogram below. So this is a Herculean undertaking, right? The sample size is just 15. From right here, sample size is those 15 lakes. This is hopefully going to be well representative of all of the lakes, high mountain lakes in the Southern Alps. And this is what their data looked like. With this in context, non-acidic that is greater than 6, it's probably kind of a pretty picture, right? It's telling us most of the lakes in the sample are non-acidic. It's not the full story because we need to do some statistics on this, find out what the averages of the sample, do some inferential statistics to see how well it describes the population. But so far, it looks like there was only 3 lakes that are classified as being acidic, between 5.5 and 6.0 on the pH scale. So high mountain lakes look like they're doing well. What we want to do is describe the shape of this distribution. But this problem is also kind of a review problem all at the same time. This is one of the harder things we do in statistics. We want to nail down both the population and the sample for this problem. This could be a problem that we come back to later on in the course to do some inferential statistics on. And if we do that, we need to know exactly what these two things are so we can give a good conclusion. I'll go first. This is the easy part. If you notice the sample size is 15, then this is always completely fine. You can say the sample is the 15 lakes selected. So sample sometimes is easier to spot on these. Sample comes from the population, and this is the one that is a little bit more tricky, like when we were dealing with that one with the capturing fish off the Pacific Ocean after the nuclear meltdown. We had to be really specific that it was after the 2011 meltdown. We had to be specific that it was fish caught off the coast of California. Here we have to be specific as well. We will say all and then something. Anyone see what should go here to describe the population well? It wouldn't be all lakes because we have to be a little bit more specific.
I know.
Exactly. We should say all high mountain lakes. If you stopped right at that point, I would say that would clarify or qualify for a full credit answer. Would anyone add anything additional?
Oh, Southern Alps.
Yeah, it was specifically these ones right here. So when they go to write up their study, they go to their big conclusions, they'll only apply to these lakes specifically. It's not going to apply to if we go to South America. It's not going to apply to these lakes in Africa, for example. We're only in specifically that one region. So population is all high mountain lakes in the Southern Alps. I'm not great with geography, but I believe this is a pretty big place. So the fact that they only took 15 is appreciable. This study could take years or decades if you're trying to study every single one of these lakes. If your study takes years to do, well, the pH here might change over the course of those years. These are moving targets. They have to get their data quick to make the data as relevant as possible. They didn't say when they got this data, but we still have a good read on what's going on by this information so far. Last thing we want to do is just describe the data they got. It's contained here in the histogram. We have to use the context, so that's the trickier thing about it. Any volunteers to give a quick description of the shape for these data? Maybe one question that I would have for you all, which is kind of tricky because most of these categories are kind of wide in a sense. There's only 15 observations, and when your sample size gets really small, the shape of your histogram gets kind of blocky. There's not enough actual piece of data to get this more fine pattern like you're seeing in this distribution, or for example, in this distribution. If I had just 10 observations, it's going to look a little bit more blocky than what you see here. That's kind of what's going on in this one. When the data starts to look blocky like this due to the small sample size, it might be hard for us to decide, is that one make peak or is that two? What would you all say for that? One or two on this one? It's kind of a tricky question, to be honest with you. I would personally say just one main peak, but that just definitely deserves some justification. Reason I would say that this is one main peak is one thing we're going to be doing later on in chapter 5 when we're starting to really use this calculator, we're starting to really use things called normal distributions, is we're going to try to put a shape on our data. For example, we want to put a shape to this data that might look about like this. We'll later on call that something like the normal distribution, something that's symmetric, bell-shaped. And we try to do that to just about any data. Uniform data is called uniform because the shape that seems to fit it the best is a flat line. Skew data has this swooping down kind of shape. That's why we didn't call these outliers. They fit the shape of this skew that we see here. And then finally, for these data, we were going to put a shape to it, might look something about like this. That would kind of give a nice shape. If we smooth it out like that, we're only really thinking one main peak belongs to these data overall. But it's kind of not the fairest question. It's kind of tricky, especially with a small sample size. So this would be one of those questions where if you did say two main peaks, I see how you're seeing it. But this would really be considered to have one main peak. So we could say, we describe the shape of this distribution using context. These high mountain lakes have a pH distribution that is unimodal. Would you all agree to symmetric on this one? I would agree with you. It's not perfect, right? This one lake right here breaks the symmetry a little bit, but we're not too worried about minor breaks of symmetry. Symmetry is an imperfect thing in real data. This is what skew data looks like, for example, or the one just above. So yeah, we could say that this is highly symmetric or just symmetric would be totally fine. Let's say it's unimodal, symmetric. And unlike the last one with the CEO ratio pay, there are no outliers. So we hit the context on this one pretty much if you just tell me that these are distribution of pH values. All this added quite a lot. Well, as long as you're connecting something from the data, all you said was pH distribution is unimodal, symmetric, no outliers, that would have qualified as well. But this is the whole thing. Here's what we mean by mention the context.
You like that word distribution?
You know, we could lose it for sure. It does come up a lot, yeah. We usually talk about the distribution of the quantitative variable, and the last section we were in for the categorical data, we had the words of, say, what was that? Relative frequency, which was the distribution of the categorical variables. So it's a word you could lose, but it does come up a good amount in the textbook. It's one of those words that are kind of almost like a just a word to kind of colorize what you're about to say. You're just talking about a variable, but it's not super specific, just all on its own. Other questions at the moment? Okay, well, we did it, folks. Sections 2.1, 2.2, and 2.3, one we just finished, all about just visualizing data. All this is in the purview of what we call descriptive statistics. You've got data, now you need to describe it to show your audience what your study is all about so they can really see what's going on. Descriptive data is nice, but it's not the end all be all, right? One thing we might want to know is, what is the median of this data set, or what is the average or mean of this data set? And that's what we're going to be doing in section 2.4. Whenever we have a data set like this, we wonder, where is the center? If we said it's unimodal, we should be able to put a number to where that mode is located at. And the next section, 2.5, we want to talk about how spread out is that data, which is just as important part of the story as well. So let's turn to those notes next. Section 2.4 on center. Starts out like a lot of sections in statistics. It's a big wall of text first before we even get to the example. But this is kind of an exciting part of the textbook because now we're about to define and actually calculate some statistics. The good news is I'm not going to ask you to do these computations by hand. That'd be a Herculean effort, and it'd be impossible to finish some problems like find the standard deviation in a reasonable amount of time. We're going to be using the calculator on these kind of problems. So section 2.4, like we mentioned last week, is one of the first sections where we're going to begin taking data like this in example 1, throwing it into the calculator to calculate quantities like this thing, the mean, or this thing, the median. So the definitions are here just to show us how it all works, what it's meant to describe. Often they come with formulas like this one as well, just to show you how you might calculate. Let's actually work with that formula just to get a feel for what it's saying. First, let me get back here. So if we had a really quick example, just ahead of even the definition here, say we have a sample. My sample has numbers, no units, just contextless, but my sample goes 5, 10, 13. We might want to calculate the average of that, and we'll say that the mean, which like we mentioned before, is going to be synonymous to the average. And all at the same time, as a particular symbol, some textbooks use X bar. Our textbook uses Y bar to describe the average. It's found by, let's look at the right-hand side of the formula first. We add up all the data. It says Y1, Y2, Y3. What their meaning is that this is the first observation. This is Y1. That's the second observation in your sample, Y2, and that's Y3 in your sample. So that's what they mean here. Y1 up to Yn is the sample data. Recall, N was the sample size. So if you're going to add up all the sample data, you go the first one, the second one, dot, dot, dot just means and so on, up to the last one. And there's telling you you're in the last observation in the sample. So using the formula, we can calculate the sample average here by going 5 plus 10 plus 13. Doing that computation is just the numerator part right here. To calculate the average, we need to know N in this particular problem. There's 3 observations, so that would mean the sample size N is 3. That takes us to the bottom part down here. We just divide our values by N after we've totaled them. So go divide by 3, and that's our average. Repeating decimal, I just grabbed some random numbers, so that's how it turned out. I'll go 9.33. And if I never tell you what to round to, then you're always welcome to use just your best judgment on that. If the data is to 1 decimal place, we would have rounded to possibly 1 decimal place for that kind of problem as well. Well, that's what the formula is saying to do. Add up all your observations, divide by your sample size. One thing that's a little annoying in statistics, however, is there's lots of ways to say the same thing. So this might have been bothering you, this weird set of symbols in the middle. That symbol there is called the summation symbol. So this is another Greek letter, sigma. This is upper case sigma in Greek. We tend to learn a good amount of Greek letters actually in statistics. This is possibly our first one we're looking into. And all that uppercase Greek letter is saying to do is literally this. Sigma means add up and find the sum or the total, or you might say the sum total, being slightly redundant. It was never a bad idea. Sometimes this symbol is literally just called the summation symbol, but that's starting to have a lot of names already. So all it is the uppercase sigma in Greek. It just means add up everything. And the thing you're adding up is the y itself. I is left there because it's saying start when I is 1. That would be the y1. Then go to y is 2. I is 2. That'd be y2. Stop when you get to n. So this whole thing is literally just saying from 1 to n, add up all of your data from y1 plus y2 all the way down yn. Then finally, the 1 over n to the left is just saying divided by n. So that's some really weird symbols. It's not something you have to memorize pat for a course on exams or things like that. It's just something we encounter a lot in the reading. We'll see it in the very next section coming up again, for example. We'll see it again when we're in, say, chapter 5, I believe, as well, when we're doing 2 quantitative variables. So that's our full look at it. Anytime this symbol comes up, I'll always show you the full formula on the right. So the only reason people in statistics like this is because you can say the formula really, really compactly. It's just a paraphrase of what the right-hand side is saying. So that's what Y bar does. It's the average. We'll often just say the mean in this class, but occasionally I'll just remind us, we mean average when we say the mean. And this was just our quick calculator example of doing that kind of thing. We're often not going to do it this way because we want usually more than one statistic. So first, we have the mean Y bar. We'll show visually what the mean Y bar looks like when you calculate it and put it on a histogram. But we already mentioned once, sometimes data is biased or excuse me, has problems like skew. There could be really big outliers. When there's skew and outliers, the mean Y bar doesn't always do a good job of describing the center of your data. Sometimes you need something else that doesn't get affected by outliers, doesn't get affected by skew, and that's the median. This is robust, meaning not very much affected at all, robust against skew and outliers. Forgot how to spell outliers. Let me try again. So if we have data that's really, really skewed, we often like to report the median. It describes the center better than the average Y bar, the mean, would do. Like we mentioned before, the median M is the 50th percentile of the data. So it's the number in the literal middle in the sense that the median is the number for which half of the observations are below what the median is, and half of the observations are above what the median happens to be. So 2 statistics, they both describe the center in different kinds of ways. Our job to really learn these is to calculate them. We'll be using these tools to speedlight those calculations, so we're not just getting bogged down on mental arithmetic or punching in numbers and trying to compute things, getting bogged down. So the calculator is already starting to become a pretty big tool for us. Any questions at the moment, folks, before we give this problem a try? Okay, so here's a weird kind of funny problem. This is real world data. It says data on tipping percent for 20 restaurant tables is consistent. So this is the author saying that she read a story and then she kind of made up her numbers, but it's based on a real study. So data on tipping for 20 restaurant tables is consistent with summary statistics giving in the paper Beauty and the Labor Market, Evidence from Restaurant Servers. So that's a real study if you want to take a look into. And here are those 20 tables. We don't know much. We don't know how high end, how highfalutin this restaurant was. We don't know if the server was a newbie or someone who's been doing this for a long time. And we don't know if the cooks were rookie cooks and screwing up the hamburgers, or if they were Michelin star chefs. We know very little about this. What we do know is what the tips were from the 20 tables. So one guy tipped $0, someone tips $27, someone tipped $105, but you know what? That could have been like a family of 12 that kind of wrecked service for the day. So maybe that was a 20% tip. We just don't know. But for taking 20 tips from those 20 tables, putting them into the histogram, this is what they got. It just says describe the shape. So here, I'm not too worried about you telling me the context. This is meant to just be a faster problem. It would be unimodal because of that one main peak there. If you did add context, you might say the tips for these 20 tables is distributed as a unimodal, but you could just be more brief and the instructions look like this. It's also skewed right. We've seen lots of skewed right data so far already. And now you have to make a judgment call. I think this one is slightly borderline, but there is a better answer to this one. Do you see outliers when you look at this data? Any volunteers for the judgment on that one? Some people are shaking their heads, yes, and I would agree with you. These are really kind of tiny judgment calls. So let me show you another one that was somewhat borderline as well, but it did have a better answer. In this section, we said that this one is not an outlier. It left the main grouping of data, which is over here, but not by very much. There's just one width of separation from this observation to the rest of the data. But over here, it's a couple distances away in terms of the widths of the rectangles in the histogram, starting to become a little bit far removed. This is one that really benefits for having an actual formula, a real rule of thumb. I keep hinting at it's coming up later. But I would say the better answer on this one, it's pretty subjective, is there is an outlier, which is that $105 table. That might have actually seemed more unusual to you just looking at the data, because being tipped more than $100 just seems like a lot of money to leave on a table or to write in on a receipt. Well, it also shows up as a pretty big outlier here. And the next thing we want to do is, well, we know it has a main peak, we know it's skewed, but we want to go beyond that and start describing this numerically now. We'll describe the center of the data where it's accumulating the most, somewhere to the right of the main peak, by calculating both the median and the mean. So we're going to go for both of them in one shot. The median will report as Y bar. This is in terms of money, so it's not a bad idea. Hang on. Looks like I missed something on there. You might have spotted that, so if you did, good on you. I was assuming these were dollars and cents. That's not true at all. It's always good to read the context more than once. This is data on tipping percent. So that was no tip. That was a 5% tip. This was a 27% tip. And this person tipped 105%. So it's like they got maybe a burger at Five Guys for $25 and they tipped $25. So that's kind of crazy. I thought that was money. So again, don't do as I did. Definitely read the context a couple times just because it's short. Doesn't mean there's hidden information there. My own assumptions were telling me it's money when it's absolutely not. These are percentages now. So beyond that revelation, we'll calculate what the average percent tip is. That's definitely more informative, right? Now it doesn't matter how big the table was or how big the ticket was. It's all about the percent tip. We'll also calculate the 50th percentile, the median. Now, best way to do this, if you have your calculator with you today, just fire it up. The first button you want to do to get all this data into your calculator so you can get both statistics in one shot is click on the stat button. Kind of makes sense, right? If we're doing statistics, that's the button to hit. You should all see this screen right here. And you know what? It doesn't hurt to leave kind of a paper trail here. This is our first use of this calculator. If you don't have yours today, that's all right. If your calculator is still coming, that's all right as well. We'll put a step-by-step guide here. Step 1, press the stat key. So come back here if you just want a refresher on doing the same procedure. I'll leave the red dot what there the keystroke is. So it should look like this. And then the very next step to take here is then press the enter key. All caps just to emphasize, well, it's all caps here on the calculator as well, so makes sense, I suppose. Your screen has to look exactly like this. Edit should be highlighted. Option 1 should be shaded or highlighted. Then when you hit the enter key, there we go, you should see this. Step 2, begin keying in the data here under L1. L1 just stands for list 1. You can put in multiple lists. If somehow your calculator looks like this, just use these keypads here to move off to the left. If you bought a used calculator, there's a good chance, especially if the student was in statistics, that you see random data that looks like this. So if you opened up your calculator and you're expecting this menu and you saw this, you can fix it. What you would do is come up here, hit the clear button. It'll look like this, L1 equals, and it's vacant. Hit enter, and it's all gone. And then you have a clean slate again. If you did like me though, before class practicing this, just as a reminder, my go-to is, if I want to clear out L1, I hit delete. And that doesn't feel nice when you delete out L1, because then you're wondering, I hit delete a bunch of times, where's all my stuff? It kind of disappears. Feels like you broke your calculator. So if you ever just let your little brother or your child play with your calculator, it might come back to you this way. It looks all messed up. So if that happens to you, this is what you do next. To fix all this, hit Stat. Scroll down to option 5, Setup Editor. Hit Enter. Now, my calculator, yours might look slightly different depending on the model that you bought. I have to hit Enter again, and it just tells me done. Something happened. So it's assuring us something is done. So go back and hit the Stat key, starting over on step 1. Hit Enter right away without hitting any of the arrow keys. And it just brings everything back as it was. So you can go up here and hit Clear, or we could go down here and just delete one by one. That works out just fine. But if there's like 50 observations in there, that gets kind of tedious. We'll mention some of these shortcuts again because we're going to be entering data in a lot. So we'll review on these kinds of things. Now, here's the tough part. We need to enter in this data bit by bit. I'm going to go column-wise just to have a decent way to do it, not forget a number, anything like that. And it's honestly kind of tough. When you're doing this as a problem on MyLab statistics, I believe it's going to come up for the first time in section 2.5. My best advice is go slow. If you're like me and you sometimes put in 16.4 instead of 14.6, not a big deal on an exam. Your number is going to be close, but it's going to be within the right ballpark. But MyStats Lab is going to mark it totally as incorrect. So go slow if you want to go fast with these kind of problems. It's going to make all of the difference. So I'm going to go column wise, 0, 10, 10, and then move on to the next column and do the same. And I'll get quiet for a moment because I'm probably distracting you right now if you're entering in the data. Okay, if you're, yeah, go ahead. Yeah, absolutely. So what you would do is go up to whichever number. Say I put in a 27.9 incorrectly, and then just immediately hit delete on that number. Sorry, say again? Oh, weird. You'd want to go down here to put in the number, but if you like, I can take a look at it with you after class to see what's going on with it. Okay. And I forget which one I did delete. That's going to be interesting. Let's see here.
I thought you said 7.9.
Gotcha, thanks. Let me put in a 27.9. So another thing you can check on your calculator is it did say that there was 20 restaurant tables. Would not have been a bad idea to think that means the sample size n is 20 on this problem. And we should see that right here. When you were putting in the last number, it should have said L120. When you hit enter, it should say L1 parenthesis 21, meaning you're about to put in the 21st piece of data. And that's your indication you're ready to stop. You had all the data. So in other words, if I go up to my last piece and it says 20 here, I have all 20 observations in, and it means I didn't miss a number. That's another easy mistake to make as well. Well, any questions so far, folks? Putting in the data? Okay, and we'll probably end class a little bit earlier today. Let me know if anything funny is going on in your calculator. I'll be happy to help out right after class. Once you have all the data in your calculator, that's what this says, step 2, begin keying in the data. Let's just put in another screenshot to emphasize that. We put in the data. Then down on step 3, we do the following. Press the stat key again. So press that again, takes you out of here. Your data is still stored. And then move over with the right keypad to calculate. So your calculator should look like this. You press the stat key again. Let me put this on the next page. Use the keypad to select that calc. So you're in option 1, one variable statistics. Calc in the middle here should be highlighted. Then press enter. So your calculator should look exactly like this. Press enter, pressing enter, and you get this screen. It should all look exactly like this. And the good news with this screen is if it's all set up like this, press enter a lot, so several times, if this is what your screen looks like. You should have L1 right here. If it's gone, if it's just nothing there or something like L3, you can bring it back. L1 is right above the number one. It's coded in blue, so you'd hit the second button, the number one button, and bring L1 back. But we'll never have a reason to change that. So pretty much it should just stay L1 and you're set for the course. You hit enter, there should be nothing here. If there is something there, just hit delete so it's blank. Hit enter again, now it's flashing on calculate, it's kind of redundant. That's why we say press enter a lot. And then a bunch of stuff happened and you get this screen. Let's take a screenshot of this. This screen actually gave us exactly what we wanted. Well, half of it. And here's our first weird thing about this course. In our book, we use Y bar, but in this calculator, this is kind of jarring. The calculator uses X bar. So that's a bit of unfortunate of a design choice by our textbook. So X bar is the Y bar you want in this problem, and it is equal to 27.3%. We'll record that up above later, but let's still focus on this screen. We also want the medium M, and it's not showing here, so that's kind of frustrating in a certain sense. Let me fix that just a bit. So Y bar is that right there. And by the way, how close did we get? Are we all getting about 27.3%? Looks like we're in an agreement. Sometimes I could just personally keyed in something incorrectly, and everyone might be at like 27.5 if I made a mistake. So if you're pretty close, then maybe I made a simple mistake, or maybe one of your numbers is slightly off. But the next thing we want is the medium M. You might know how to do this by hand, but in this course, we're going to make the calculator do some of the heavy lifting on this one as well. Notice how there's a down arrow. This is something that's kind of easy to miss here. Next, press the down key on the keypad. The down arrow is just telling us there's more stuff. There's a whole bunch more stuff. Press the down key a bunch of times, and it gives us the remaining statistics. Whoa, I just needed that once. Hoping to get that on one page, but you know, we'll make it 2 pages on this one just so that we don't scrunch things down too much. The median is this right here. They kind of spell it out. MED is the first 3 letters of median. And this came out at 21%. This is telling us half the tables had a tipping amount above 21%. Half the tables had a tipping amount below 21%. And this is telling us the average or the mean is 27.3%. They're actually pretty different, right? By about, 6.3%. So it's kind of amazing in a certain sense. And this is what we'll come back to discussing next class, how it relates with the histogram. But really, this was really our first rodeo at putting numbers into the calculator and getting values out. Any questions at all, folks, before we call it a night? Okay, well, have a great night, folks. On Thursday, we'll finish off these notes, possibly start section 2.5 as well. I'll post a quiz. The quiz is going to be basically doing what we just did. I'll give you some more random data and ask for the mean, for example. So pretty similar to what we just practiced. But have a great night. I'll see you all in Thursday's class. Oh, and if anything worked a little bit weird on your calculator, I'll be happy to help out. Hey, you said it wasn't deleting for you.
Yeah, so it's just not like showing anything. No
Oh,
lanes or.
That is interesting.
Yeah.
So it is the TI-84 plus, so it should be giving us the same thing.
You
What
know,
happens if you hit just the stat key?
So, if I just hit the stat key and then press enter, it just takes me back.
Okay, so hit the stat key again to get back to this menu
Mhm.
and try doing this one right here, 5.
Is that a better here?
Yeah, and hit enter a couple times until it says done. Okay, so now go back to stat. Hit enter. Did it bring it back?
It did.
Okay, cool.
Awesome, maybe, yeah. I just probably haven't set it off.
Yeah, possibly.
That's fine.
Got, someone probably let their kid play with it. I bet you anything.